Right. Okay. Yeah. Good afternoon. So thanks for the introduction, Joachim. So this is an introduction to statistical dosimetry. So something presumably a bit different to what you've heard so far today. So I will also stay a bit further away from the computation and stay a bit more on the conceptual side of things. And I should say also that this work has been influenced by some people and institutions, which I'm just thanking here or mentioning here on the title slide. Yeah, so the context of this talk is radiation. So radiation is energy in the form of waves or particles that travels through space or material. But when we talk about radiation, we mostly mean ionizing radiation. So that means energy which carries enough, so radiation which carries enough energy to ionize atoms or molecules. So you have here an example of a photon which kicks out an electron, and then an ion with a positive charge remains. And ionizing radiation can cause serious damage to cells, tissues, DNA in the human body, for instance. Okay, dosimetry is the science of measuring or estimating the radiation dose absorbed by an individual. So the absorbed dose is measured in Gray, so that's a relative measure, that's joules per kilogram. So when people say dosimetry, they usually mean radiation. So you can also do dosimetry for other things, like particular matter, for instance, but then you would say that. So if you say dosimetry, you would usually mean radiation dosimetry. There are different types of such dosimetry. So there are personal dosimeters in use. So if you think of people who work in a nuclear plant, for instance, so they would usually wear a dosimeter, which would indicate in real time the radiation dose to which they are exposed. But of course, that's not always the case. So if you think of members of the public, they usually don't wear a dosimeter. Or if you think of an accident, well, we may think of large-scale accidents here like Fukushima, but also small-scale accidents simply or incidents really, simply that in some laboratory, somebody has not really followed protocol. But then they usually will not wear a dosimeter in that moment. So you need somehow to quantify retrospectively the degree of radiation that got absorbed. Here are then again several ways of doing so. So there is biological dosimetry. So here you try to somehow quantify the damage by looking into DNA, chromosomes, proteins, so quantifying the damage inside the human body. Or there is physical dosimetry that here people look really at things like clothes, shoes, mobile phones, etc., and look what happened to the material in there. So there are some people here actually in Durham in the physics and archaeology department who do that. I'm not talking about this, so I'm focusing here on biological dosimetry today in this talk. And this is also known as biodosimetry. Okay, so biological dosimetry needs a biomarker, so short, a biological marker, which you can define as any substance, structure, or process that can be measured in the body or its products, and which influences or predicts the incidence or outcome or disease. So biomarkers may typically do one of two things or a combination of those. So they may measure directly the damage caused by the radiation inside the human body. So really you look at counts of aberrant, so damaged chromosomes per cell, or you try to look at the response that the body does towards the radiation exposure. Then you usually look at proteins. And either way, this usually results in counts of something, chromosome aberrations or protein foci or something like that. But usually these biomarkers result in count data. Statistics comes then into play when establishing the link between that count and the absorbed dose. Of course, after all, what you usually want is to obtain an estimate of the radiation dose from that biomarker. So let's start with one particular class of biomarkers. These are cytogenetic biomarkers, so biomarkers which somehow look into, let's say, features of the nucleus and to damage that has been caused by the ionizing radiation in there. So the cells that are usually considered for that purpose are blood lymphocytes. And two of the most commonly used cytogenetic biomarkers are dicentric chromosomes or micronuclei. So what you have on the left-hand side, these are dicentric chromosomes. So imagine that a human body got exposed to radiation, and then some damage has occurred, and the body has tried to fix it, and sometimes that goes right, and sometimes it doesn't. And when these repair mechanisms haven't quite done what they should do, what you see here are that you see here chromosomes where you have that arrow here, which have like two centers, right, which are connected at two places. One says they have two centromeres, and that's a dicentric chromosome. So that's an aberration, so that's wrong. So one can count these per cell, yeah, and then that count is informative for the radiation dose. So these are dicentric chromosomes. Another one are micronuclei. These are like nucleus fragments, so little pieces of nucleus, or pieces of chromatid, which sort of get thrown out of the actual nucleus and then stay around. It's not the big blue dots that you see here on that microscope image. It's those little tiny blue dots beside the big blue dots. So you see immediately that these counting problems are not always straightforward. So the dicentrics are a bit easier to count. The micronuclei are really hard to count because there's overlapping and all sort of other things going on. So in order to understand how actually radiation dose relates to such a biomarker, one needs to do laboratory, so in vitro experiments. So these are data from Public Health England, which were produced in order to create a calibration curve for dicentric chromosomes. So what was done here, that let's say a batch of blood, yeah, was divided into 5 pieces, and then each piece got exposed to a certain degree of radiation that you have here. Here you have 1 gray, 2 gray, 3 gray, 4 gray, 5 gray. Then for each batch, one has examined a certain number of cells. This is this number here. So for those who got exposed to 1 gray, we examined 2,000 cells. And then we counted the number of aberrations in there. So for instance, here we see that 1,715 cells did not carry any dicentric chromosomes at all. 268 cells carried 1 dicentric chromosome, 15 carried 2 chromosomes, 2 carried 3 dicentric chromosomes, and so on. Yeah. So what you see here, that's the distribution as you go down here. The distribution tends to shift to the right. Yeah. So the higher the dose is, the more dicentric chromosomes we seem to get. So this seems to indicate that the conceptual link is somehow sound. Yeah, the more the higher the radiation exposure is, the more dicentric chromosomes we have. Just you also see there is huge uncertainty in that process, so that will be by no means a very straightforward, clean estimation problem. Okay, so in order to fit an actual dose response curve, you need a model. So these are count data. So a natural choice for the response distribution would be the Poisson model. So you have here a Poisson density written down. So Yij would be an individual count of dicentric aberration in the J cell of blood sample I, where I is that index going down here. Okay, for that model, the biodosimetry literature suggests a quadratic model with identity link. Identity link simply means that I don't have any transformation here. So if you would put the average statistician onto that problem, they would tell you, well, these are count data. This is a type of generalized model. You need a log link. People in the dosimetry literature don't like that because there is a physical argument for this relationship to be as it is, which has to do with the number of interactions as the radiation passes through the nucleus. I won't give that physical argument here, but there is a physical reason for there not being a log link here. In order to estimate the parameters, one needs to set up the likelihood. So we have here simply a product of all the densities of the individual counts. This is then a product of these Poisson densities. But the point to make here really is just what you get here in the final likelihood expression, that it really depends just on the NIs, which are the number of cells examined for each dose level, and the total count per row. So this sum over j, yij, is really the total aberration count per such a row. So in this case, 1,715 plus 268 plus 15 plus 2, and so on. Everything else doesn't matter. So this is, well, it's the statistical concept of sufficiency is really behind that. So that means in practice, in order to fit such a calibration curve, we don't really need that big data table. We can just sum things up here within each row and work on the aggregated data level. So this is then the summary that we have here. So here we have the number of cells considered, and then here we have these counts. So if I produce now graphically these ratios, so I'm looking here at yi divided by ni, okay? So I'm not actually plotting yi, but yi relative to the number of cells, so the number of dicentric chromosomes per cell. And then we see here something what you could call an empirical dose response curve. Yeah, so we see already that some quite clear structure is actually building up. So despite these apparent large variations here within one row, we see that actually a quite solid dose response curve seems to be materializing here. Yeah, so this is without fitting any models. I've not fitted any models. So if I now write down the model in terms of aggregated data, so what I'm really modeling is the expected number of aberrations per cell. Yeah, so I'm not really interested in the total, in the raw Poisson counts. What is really modeled is the number of aberrations per cell. This is described by the quadratic term. This is then fitted through Poisson regression. So that's a special case of generalized linear models that can be fitted through maximum likelihood through an iteratively weighted least squares algorithm. I don't want to go into details here, so that is GLM theory. So if you do that, you can obtain estimates beta null hat, beta 1 hat, beta 2 hat, and you get your fitted dose response curve. And you see this fits actually quite nice. It's possibly a bit too good to be true. It also comes from laboratory data. But in general, it is the case that for this dicentric biomarker, those response curves are relatively stable. Also, if you obtain these curves from 3 or 4 or 5 different laboratories, they will vary, but they will not vary a lot. Yeah, so that is a relatively stable feature over different people, different laboratories, different equipment partly. So these are relatively stable. So they can in fact be used quite sensibly for dose estimation. Well, how are they then actually used for dose estimation? There is one difficulty to note. Yeah? So what we have produced now in all this philosophy here, yeah, is a model for the dicentric count yi given dose. Yeah? Of course, in practice, we want to do the inverse thing. Yeah? We want to estimate the dose given a count. Yeah. So what would that mean in practice? Let's do an example. So let's assume we have this red calibration curve, this laboratory curve that we just derived. And now a patient has been admitted to hospital due to some potential radiation exposure. And let's assume that a sample of 200 lymphocytes was analyzed, and that has led to a total of 150 dicentrics. Now, all what we need to do is to compute this ratio here. Yeah, 150 divided by 200. So it's not really relevant within those 200 cells how exactly that distribution was. We just look at the total count. Yeah, that was this sufficiency principle. Then we go here in our calibration curve horizontally until we reach the curve. We go down, and this here at the bottom gives us the dose estimate at around 2.7 or so. Yeah. So this looks reasonably simple. What is happening here mathematically? Well, also, this is not really a big problem. So assume the observed ratio, let's denote this as R star is Y star by N star, yeah, Y star and N star being, for instance, these two values or any other ones. This is then simply equated to our calibration curve. And well, every student in year 9 or year 10 of secondary school should be able to solve this problem. So we just can put our estimates in from the calibration curve and our ratio, and we get, in fact, a dose estimate. So inverse regression is something quite simple, really, conceptually. It gets more tricky once that you start worrying about uncertainty. Yeah, of course, I have an estimate here, but now how precise is that? So 2.7, what does it mean? Could it be 2? Could it be 3? Could it be 5? Yeah. So how can we quantify the uncertainty related to that? And when thinking about this, one firstly needs to acknowledge that there are two types of uncertainty coming into play here. There's firstly uncertainty due to the estimation of the calibration curve as such. Yeah? So we have estimated that curve that came out of generalized linear model theory, but these are estimates, these are parameter estimates, so they come with some uncertainty. Yeah? So you can think of some confidence bands here spanning the actual calibration curve. But then also this value Y star, that will also can be thought to be coming from a Poisson distribution. And if it comes from a Poisson distribution, it comes with Poisson sampling error. So there will be additionally here on that vertical axis some random variation. We happened to observe 150, right? But we could have equally have observed 140 or 160 with some Poisson sampling luck. Yeah, so it could have been slightly different. So there's coming an additional layer of uncertainty on top of that. Well, looking at these images, if you present in this way, one can quite easily, I think, with some engineering type skills, infer how somehow these two layers of uncertainty can be added. And this is actually what is known in the dosimetry literature as Merkel's method, that simply connects here the lower blue band here with the upper green one, and here the upper blue with the lower green one. So it maximizes really the uncertainty on both levels. And then we project these down onto the horizontal line. We see then that in this case, a 95% confidence interval would be given by 2.04 to 3.33. That is not really difficult to implement, and this is also the official uncertainty assessment routine suggested by the by the International Atomic Energy Agency. What one is doing here, so you can feel it by looking at this image, that one is probably slightly over-counting, like overstating, double counting, and to some extent the uncertainty. So this interval is really a bit wider than it would actually need to be. So people have recently started looking into approaches which are a bit more principled, and this includes Bayesian approaches. So this is a quite condensed slide, and I've packed the entire methodology on there, also partly because I didn't want to spend too much time with it. But let me still try to go briefly through that for those who have a little bit of a Bayesian background. So Same notation as before. We have a potentially exposed patient. We count the centric total, or Y star, in a sample of N star cells. And from this, we can obtain something like a test data likelihood. Yeah? So this you can see in complete analogy to this thing here. Yeah? But just for that particular blood sample from over N star cells from that particular exposed person. Now, one needs some collection of priors. Well, there are different things that one can do here, but what is done in this approach here is that the calibration curve is really taken as fixed and is put in some plug-in manner, yeah, is placed into the prior. There is some uncertainty assumed around that calibration curve, and some prior for the dose that will typically something like a uniform distribution between 0 and 5 Gray. Having that prior, we have then our test data likelihood. These are then multiplied with the prior. And if you remember the previous talk, there you were told that the denominator is usually not really needed, because typically we can identify the posterior only from this product here of prior times likelihood. And exactly this is happening here. So I've not written down the denominator here. Integrating over lambda, what we are not really interested in, gives then well, what a Bayesian would call the posterior predictive distribution, and what in that paper here was called the calibrative density of X. And this is really the posterior distribution of the dose given our observed decentric count. And also, in difference to the previous talk where you needed the Monte Carlo to solve that, here, in fact, this integral has an explicit solution. So not always that computation is needed. Okay, right. So let's return to the same example as before and apply this. So we have the patient sample. We have observed 150 decentric chromosomes in 200 cells. We have the same dose response curve as before. This is then thrown into that machinery. One can do that relatively easily with R package Radia. I have not provided that code here now, but if you look into R package, into that package, it's well explained how to do that. And you get immediately a posterior distribution. And if we now, well, this distribution gives us two things, right? So it firstly indicates us where the point estimate is, presumably at the mode. And secondly, it will help us to quantify the uncertainty, because we can specify some intervals here, some credible intervals, to tell us where the dose estimate is likely to reside with high probability. So we see the point estimate is at 275, which is very close to our previous estimate from the inverse regression, which gave us 2745, I think. If we look at a credible interval, yeah, so we see that the dose, and here in a Bayesian context, we can actually say that the dose with 95% probability, yeah, lies between these two blue bounds. They're actually vertical. It's a bit of an optical illusion that they seem twisted, but of course they are vertical lines. So we see with 95% probability the dose comes to lie in this interval. And here you also see, again, what I said before, that the official methodology is really overstating the uncertainty quite a lot. So the Bayesian one, which I think is a bit more principled here, comes to a somewhat more precise result. And if you think about a triage situation in a hospital where you have certain procedures which kick in, for instance, if the patient got exposed with, let's say, at least 2.5 Gray, then this can have a practical difference to know where the lower bound or the upper bound is placed. Okay, right. This was the dicentric assay. So this is still and generally considered as the gold standard in biological dosimetry. So the reasons for that I have already alluded to briefly, but let me just repeat it here. So there is relatively little inter-individual variation. Yeah. So if person A or person B get exposed to the same radiation dose, then that will typically incur a similar degree of damage in them. There is relatively little overdispersion. The overdispersion is the variance to mean ratio. So that is relatively close to 1 here. And this is why the Poisson model is appropriate. It can be adapted to deal with partial body exposures relatively easily, even so I'm not going to talk about this here. And it's well supported by software. Well, I've mentioned Radia, and there are also other software packages that I come to speak on about later on. I should also say what is not written here, that it's quite that the biomarker is radiation specific. So, well, it doesn't depend too much on the type of radiation. This is good, but you don't really get decentric chromosomes or anything else. Yeah? You don't really get it through stress or because you have painted your house with some paint, or you have taken on some other chemical or whatever particular matter. Yeah, so it's really triggered essentially only by radiation. So that's another advantage. There are some disadvantages. Well, as said on the first slide, the scoring, so the counting can be difficult. You may need to wait quite a lot of time until you can actually apply it, because until you see these beautiful chromosomes here, these decentric chromosomes, you need to wait until the metaphase of the mitosis, because otherwise one just cannot see them. And this can take 3 days, which can be quite a lot if you're worried about getting exposed or having been exposed to radiation and you would like the answer. There are also some potential biases involved. For instance, if the cell gets hit so strongly by radiation that it got essentially destroyed, there will be no mitosis and no metaphase, and there will be no chromosome anymore to observe. Yeah. So for very strong radiation exposure, the cell may break before you can actually observe the damage. And similarly, if you wait too long, the cell may got repaired already through the repair mechanisms, so that you can't see the damage anymore. But here we are talking about really several months before that would have happened for this assay. Okay, so but this brings me to some alternative biomarkers, which I want to briefly mention here. So there are the micronuclei that are where you briefly saw an image further. Micronuclei, you get to a result a bit quicker than for the decentric assay, but the variability is just really so much larger, and that is partly through to the difficulty of counting that I mentioned. Here actually also come quite a lot of imaging work on imaging technology comes to play here, that I'm not going in detail. There is a translocation assay, which looks at exchanges between pieces of DNA. That has the advantage that is a very stable assay, so you can use that one years after the exposure, and it will tell you whether you got exposed or not. There are assays based on gene expressions. There is the qPCR, polymerase chain reaction technology. Yeah, that's really the same the same technology in principle that's being used for COVID PCR tests. There is methodology based on direct counting of DNA or mRNA molecules. And a new family, these are protein-based biomarkers. So these don't really quantify damage, but these quantify the activity of proteins which try to repair the image. There is the 53 BP1 foci. So this is known as a, or otherwise known as a tumor suppression protein. And then what I'll look at for the rest of this talk today, these are gamma H2AX foci. So now let's delve into proteins for the next 10 minutes or so. So histones are a special type of proteins which help to package the DNA double helix. So you have here DNA, and typically this DNA is wrapped around 8 of such histones. Two of each are called H2A, H2B, H3, and H4. These form a so-called octamer, and then the DNA is wrapped about that, and this actually helps to wrap the DNA so that it can be efficiently squashed into the nucleus. So we are interested here in a special subtype of the H2A histone, which is called H2AX. That is known as a DNA damage repair protein. Yeah? So as soon as there is some damage in the body, that H2AX protein tries to solve it. So it is known that if a radiation-induced double-strand break has occurred, the H2AX histone reacts with phosphorylation. So chemically, that is the addition of a phosphoryl group to the protein. In this state, it's referred to as gamma H2AX. And this phosphorylation, this can be made visible through immunofluorescence microscopy. And what you see really here is for each double strand break, you see a foci. Yeah? These are these little red dots, and these can be relatively easily counted. So that's easier as for the micronuclei, because here we don't need to count the little hidden dots, but here the big dots is the real thing that we're counting. Yeah? So, and here again, typically one examples a collection of 500 to 1,000 blood lymphocytes. This is shown here on a picture. So these are put on a slide, and then one can either again through imaging technology or manually, one can count the number of foci per cell on each slide. Okay, this gives then data, calibration data of a very similar character that we saw before. So perhaps I should briefly make that link. So what you see here is really just the same what you saw here on this slide, where we looked at the decentric assay. Yeah? So these are aggregated data, so foci per cell for a given slide. But I have now, so each of these point corresponds to a slide. Yeah? So I have now quite a few of these slides. So I have now a bit more calibration data here. And I've plotted them all together, that one gets a bit of an idea of the uncertainty of those. And also what you see here, the red points are after 24 hours after exposure, and the black ones are 1 hour after exposure. And you see that something quite dramatic is happening here. So the number of these foci really reduces very quickly. Yeah. So after 24 hours, really not much is left. And if you go further, the line or that curve here would become so horizontal that it would be difficult to detect anything. Yeah. So much in difference to the decentric assay, the H2X based dose estimation has to happen relatively quickly. Yeah. But you see that there's considerable variation. So even among these foci per cell yields, so uncertainty quantification will again be crucial. The fitting of these curves is not complicated at all. So we can just do again some Poisson regression. You might consider a quadratic model as before, but if you look at that, it's actually not really necessary. And we looked a little bit into this. So really the quadratic model really just increases the variance. And so also the literature seems to settle on that quadratic curves are fine for this protein biomarkers, so that linear curves are fine for this protein biomarker, and that quadratic curves are not really needed. Yeah. So here you have 2 examples for linear calibration curves and the corresponding quadratic curves. However, there is another problem. So I mentioned that for the decentric assay, the variance to mean ratio was more or less equal to 1. Here, it's now much larger than 1. So for instance, here, what you see here is for each of such a slide, is just displayed the mean on the horizontal axis of all the counts in that slide, and then on the vertical axis, the variance. And if I take any of those, for instance, this one here, I have here 200,000 divided by 4,000, that is more or less 50. Yeah. So I have a variance to mean ratio of approximately 50. And if you if you fit a linear model and then obtain a model-based dispersion estimate, so this is in the statistical literature can be obtained by dividing the deviance by the total sample size minus 2. You see also this is somehow around 50. So there is a massive dispersion for the data set. So you cannot just use Poisson regression. So the lucky answer is, without giving too much detail here, fortunately, if you work out for such a situation where you have such an overdispersion, the overdispersion which is simply expressed by the variance is not equal to the mean, but the variance is phi times the mean. If you work out the score equations, that means the derivatives of the log likelihood, you see that phi just cancels out. So I could multiply here with that phi and it disappears. So that means even under overdispersion, you can still fit a Poisson model, you can still fit a Poisson regression, and the parameter estimates don't change at all. So that's great. So from a pure calibration curve estimation point of view, you don't need to worry about this. You can show that the standard errors do depend on phi, but you can adjust them retrospectively. So in practice, we see that this overdispersion is not really a big obstacle. So you can still just fit a Poisson regression as usual. And then in retrospect, you just need to somehow to estimate that this dispersion, for instance, through the deviance, and you just adjust your standard errors appropriately or accordingly. So that's relatively easy, fortunately. What is more tricky is the uncertainty quantification. So the inverse regression is even more easy now, right? So if we only have a linear calibration curve, what I said is sufficient. So let's assume the patient sample somewhere gives you a foci to cell ratio here. You just go here and go down. So this is the linear regression inverted. So that is extremely easy. The uncertainty quantification is a bit more tricky. So that Merkle method thing doesn't work at all anymore. So what's done here is, what is really the I find nicest and more general approach to uncertaintification in general. So if you have any function of anything, and you can quantify the uncertainty of each of the individual things, in this case, the y star, the a hat, and the b hat. You can use the delta method, or it's really just a part of the delta method. Yeah. So all what you need is you need to work out the partial derivatives of that expression with respect to each of these things here. You need to square it and then multiply it by the corresponding squared standard errors of the individual things. There would be some cross terms, but usually they are relatively small, so some covariance terms. So these are only the main terms. But this here is really a very useful general principle to work out really the uncertainty of a function of anything. So if you want to take anything back from that talk here, what is useful in general, then it's this method. So that can be worked out relatively quickly. All these standard errors can be worked out for the Poisson sampling error here. One needs to take a bit of care to put the dispersion index back, but that's just a special feature of this particular problem. But this can be worked out, so that's nice. So we are able to work out the uncertainty here. Just one more technicality here. So on top of the general variability here for which is really variability down to individual blood samples, it's unfortunately also the case for this assay that the entire calibration curve may be very different for a different laboratory equipment, scorer, etc. So in practice, it needs to be validated somehow. So before you actually estimate the dose in a particular lab, that lab should produce some reference samples. And so to irradiate a blood sample intentionally at a known dose and look at the radiation exposure that you or at the foci per cell that result from this. If this is then outside the prediction intervals that we would expect, then it would actually be advised to create a new calibration curve. So here one needs to take care again. So in some work that we actually did here in that to solve that particular problem, some web apply got produced at Durham. So perhaps I can briefly show that. So this is here, the dose estimate H2X. So you need to tell the software whether you have your own calibration curve or not. Let's assume I don't have my curve, then I need to take the built-in curve. I need to tell whether I have extracted my foci measurements 1 or 24 hours after exposure. I also need to tell whether I have such reference samples available to check it. Let's assume I don't have that. And let's assume I'm at 24 hours. That what is called here Y is what I've called R in my talks. So the foci per cell, let's assume this is 200. And we do that, and we, well, get in this case, well, that was probably not a good example. Let me go with 20%. We would then still get a relatively large point estimate of 10 gray with a standard error of 0.8. And we also get a plot which gives us the estimated dose and an uncertainty estimate from this. Yeah. So this is a little tool that what we can play around with. You can then play around with situations where you actually give your own calibration curve, or where you do have reference samples available with which you could validate your curve. So for instance, in this case, we got a message that the calibration curve used here was not actually validated for the data. Right. This was a simple example. So I'm coming now to the summary. So summarizing, well, I've shown now 2 assays. I could have shown more, but I think 2 is more than sufficient to illustrate the problem. The centric one is the most robust one, but it takes quite a long time, and it's very labor intensive to actually arrive at an outcome. The H2X has the opposite problem. You get a much quicker dose estimation, but you have to do it quickly, because if you wait too long, the information is gone. There is still a gap, because typically the time when people want their estimate is when they actually get worried about this is after a day or so. And this is when this one is not applicable anymore, and this one, the centric one, is not applicable yet. So the public health laboratories are actually trying still to close that gap somehow. So the gene expression assays may be in a position to do that. Combinations of biomarkers may also be the way to go. I should also say one more thing here in terms of the methods. Well, there is a bit of software here, but you have seen that all of this is really not really computationally intensive. So the methods are relatively simple, but it's very fitly. So what is much more important is to do it correctly than to do something which is computationally problematic. Yeah. So one needs to do it carefully, and one needs to think about the physics of it, the biology of it, the statistics of it, and the mathematics of it, and then to do the right thing. It's not so much a computational or a programming challenge, than rather a challenge of putting the different sciences together in the right way. Right, I have one final slide here with the references, and I think that's it. Thank you.
Thanks, Jochen. Well, I will stop the recording. If people have questions, please, we have time.